So we are going to look at it, and you will see later here or later that some of the concepts that you will use so wide also in discussing a lot of mathematical aspects, a lot of mathematical structures, a lot of a number of fields, mathematical fields and areas. For example, topology is very much related to geometry, how we call it geometry, algebraic geometry, for example, is very also related to algebra, these structures, groups, rings, and so on and so forth. You'll come to see them. So, but for your own sake, we are going to start with the general overview of the aspect of topology that will help you to grasp the main concepts. The main concepts of topology. So we may begin with definition then. I have to also warn you that you may need to do a review of your set theory and other related mathematical concepts. Well, I'm sure you have learned at the lower levels, which you are going to use here to explain a lot of concepts which you are going to do as they relate to topology. Because the building block of topology is set. You have to have the set first before you now start to construct topology. So we start with set in our definition. We say let S be a non-empty set. Okay. So you begin first with a set. You get a set, a non-empty set, and then from that set you start to do some construction that will allow you to form a non-empty set first. Okay, and define tab, somewhat like an operator now on set, on your set. Okay, on S. Okay, such that tau has the following, or let me say satisfy. You require this tau you define somewhat like an operator, and for tau it's nothing but collections of open subset of S. Now you have a big set S, and you now subdivide into smaller subsets. Now the collection of these smaller subsets are what constitute your tau now. Okay? So you require your tau to satisfy the following. Number one, that for SIs in tau, big collections, SIs, subset of S, of course, in tau, members of tau, union over N, or let me even say over I, okay, of SIs should also be in tau. Okay? And for some time you don't even require to say you to put I, that means you can just over infinity from I1 to you can even allow I to run to infinity. All the collections, collect all of them, they will always be in tau. And number two, the same for the same SIs, intersection I from 1 to. So you require intersection, you require finite intersection. This one may not have to be finite, but in intersection you require a finite SI should also be empty. Okay. In fact, I should have mentioned that you also require the conditions Actually, I put this number 1, I think, but it's okay. I think you can. As at phi, the empty set is in tau. I should also require S itself to be in tau. Okay, then tau is called a topology. On S, sometimes we call it standard topology. We call it this standard. It's a standard topology on S. Okay. Yes. So what has this told you is that the building block of the topology is set. You start with a set, and then subdivide your set. If you are doing it step by step, get a set first, and then subdivide your set into subsets. Then you now require these subsets to satisfy these conditions. Now, you have a topology. And so you can clearly see now that topology is something which you always have around you. So it's so vast, so many, so much that you don't even know how many there are. And you don't even know how much they relate. I can give you instances for example. So we can clean this row if you are done. So clean this and go to examples. Okay, examples. 1. If you look around you, you are sitting in a space. Okay, you are sitting in a space. Now this space actually, you can explain it some bit, some sort of, give it some algebra, some geometric sense, and by the time you do that, you find out that you are actually constructing some topology around you. That's the best form of expressing. As we are sitting here, we have a structure here, which is a space. Now this structure, we can say it's also a topology, because if we subdivide this structure, for example, if we divide this first row, second row, third row as subsets of this building, we can use these subsets to look at our axioms or properties. And by the time, for example, if you unite all these subsets, you get a structure within here, isn't it? If you take the intersection, you will still get a structure which is here, isn't it? The whole of this structure is also here. So S is here, isn't it? The empty set, you can use some connotation to define empty set to mean maybe a point. Okay? A point means it's not a set. It's only one point. So you cannot move around. So you don't talk of open set, because like we call topology collection of open sets. Now if you have a point, you don't have a set, because point is only an element. So you can define that to be an empty set. So you can see clearly that this being here, it's a lot of topologies. Because even where you are sitting, you can subdivide it. Isn't it? If you take this as a space, you can subdivide subspaces of rectangular structures, and then the union's intersection will still be here, and you have a topology. And so on and so forth, so that you now talk of so much about topology, including talking about neighborhoods now. Yes, so that's one of the examples we have. But so and another example is the power set. Let S be in an empty set. Okay. It can be readily verified that the collection of subsets of S, okay. Normally we do not all subset, all of them, okay, all. Normally denoted by P of S, okay. Isn't it? Or sometimes we write it as 2 raised to power S. We call it power set, called the power set. Defines a topology on S. Okay, you can verify this, you can prove this. Before you can go along. Okay, to another one. You can go around the full process. Take S and an empty set, it's big or small, and I get all the subsets of S. We call it power set. Isn't it? Now you can easily verify that this collection actually is a topology on S. Okay? So you can look at this. For example, supposing your S is set A, B, C, or I give simple example. It has these elements, and the power set of S is what? P of S will be what? The set A, set B, set C, set AB, set AC, BC, ABC, empty set. Okay. You can easily check that this collection here satisfies your. For example, number 1 is clearly you can see even without checking by just viewing this, clearly you can see phi is in tau, isn't it? It's in P of S, isn't it? P of S is our tau now, isn't it? And S is also S, which is also A, B, C, is also in P of S, isn't it? C phi, this is S, isn't it? What of the union? Also, do we write or we cannot capture? Okay, now we can clean this one and write off. The union over I of Si is also a subset of power S. You can unite all this. You take the union of all this, A union B union C. You will get the highest you get is what? In fact, it's going to be, if you take all the collection by definition, it's going to be S itself. If you unite this, you recover your S. But S is already in pure S. What of the intersection? If you intersect over I, SIs, intersect all this, what do you get? It's actually the empty set. Because by saying intersect with empty set, you get empty. But empty set is also in pure S. So you can see that all your laws are satisfied. So therefore, P of S defines a topology on S as being an empty set. This is just ordinary definition of S. You can also give example of your class. Supposing you have the elements here, And I'd say on every row is a subset. This is S1, S2, S3. Then if I collect all of you, I get the class. The empty set may be the empty seats, that row which has nobody inside. Because it's still in this class, isn't it? Maybe those who are absent. So you can use that also for an example of topology. Okay, let us go to geometry now. If you look at this building, for example, we take the lines, it's a rectangular shape. Of course, you can segment it into subsets, isn't it? By the time you do that, you have also another collection of sets, which can also form a topology. Yes, the Euclidean geometry, for example, take a straight line. If you think this one is too simple, you can take a straight line. You can take simple straight line. Okay? That's your arc, isn't it? Straight line. You can take the arc, or E, whatever you call it. You can form topology on this, but by subdividing the R into intervals, A1, B1, A2, B2, A3, B3, A4, B4, and so on and so on. Okay, so the collection, so you say let R be the interval from minus infinity to infinity, isn't it? And define tau on R to be open intervals. AI, BI. Of course, it's contained. Each one is contained in R, isn't it? No, it can be verified. It can be verified that this collection. If you like, you can give it a name. I don't know whether you call it maybe CI, isn't it? Or CR, which is the collection of what? All AIs, BIs, with what? AI, BI, members of R. If you take all the collections in form of say, forms a topology. On what? On R, the real lines in the Euclidean plane. Okay? Then you quickly verify your axioms 1 to 4. In fact, you can also take a two-dimensional plane, the R square, and you can form n-dimensional planes are also topologies, depending on your M. So that's why I told you that topologies are so many that you cannot count. There are so many. As you are standing, if you stand up as a person, you are also made up of so much that we can characterize as a topology. So in manifold theory, we look at how to reflect you as a topology, isn't it? We can, for example, we can consider your face, your arms, your legs, your whatever, as subsets of your own self. And then look at how we can look at it. For example, if you are going to form a chart of you or a photo of you, we are going to use your topologies because we are not going to produce you, but we are going to reproduce a replica of you. That's your topology. We will reflect on points of your body on something, a very piece of paper. and that's topology. Okay? So we have so many examples, so many of them. So maybe I think you can do this as an exercise. Okay? To verify that this is the topology. Okay, you can verify that Rn is a topology. Okay? You can feel like you can try this. It's very clear from here. You can see if you unite all these intervals, all of them, you have to unite all of them. The highest you can get is R, but R is also in CR. If you take the intersection here, all of these will be shrinking up to here. We'll meet a point here, which is not an interval. So you can call this an empty set. It's an CR. Each interval is in CR because each interval is an opposite. Each AI, BI. Of course, it's in CR because each of them is an open interval in R. Isn't it? So it's very clear to see that this is already a topology on the straight line. So I will give you next definition now. I have given you some hints now. We can go to definitions. Definition. Okay, the pair, maybe I can use X or S, whatever I use. Sometimes I use X, X with tau on it, of N on empty, consisting N on empty, set X, okay, and a topology, tau, defined on X. This one is called a topological space. Underline this, topological space. Why? Because you have a set, and you have an operator which is operating on subsets of the set X. So it's like a space now, isn't it? It's not, marking is not, it's different from what you used to have when you have the groups, for example, with binary operation. These are one group of binary. This may not be a space because we are talking about elements now here in binary operation. But in tau, we are talking about a subset of G, okay? Pairs of subset of G, okay? And you also have a sense, you will come to see when you talk of matrix space topology, that this space can change to something like X and D, where D will be a metric, or a geometric distance between 2 points in the space. You have a space first, then you start to cut the space into distances D1, D2, D3. Now how these D's act on your lines or your space will also matter, because you need to satisfy that condition. Then you say you have a metric space, okay, with triangular inequality. So this is topological space, actually. Yes, so in your lecture notes, I think we can look at more examples here, maybe. Now we have another definition. discrete and indiscrete topology. Okay? So I have this, maybe we can clear this one, give you another definition before we go to more examples. So you still let S be a non-empty, okay, and tau, a topology defined on S, okay. Then, number one, the topology, okay, with fewest number of elements, okay, is called the indiscrete, okay, indiscrete. While 2, okay, yes, while 2, the topology with highest number of elements, okay, it's called, no, sometimes if we denoted by 2s, called the discrete topology. Okay, so that topology was the highest, like we saw before. All the collections of subsets is called the discrete. That's with the fewest is called the indiscrete topology. Okay, so you can see, we can clearly see in the example we took that. What is the discrete? The 2s, isn't it? The 2s, all the collection. But what is indiscrete is the file, the empty set. All those topologies with just one element. This one, the fewest number of elements. When you say A, B, this one is just indiscrete. That's the one with the A, B, C, for example. This is the indiscrete. This is the discrete. This is the indiscrete. And you can see clearly, even from the definition of discrete and the discrete mathematics in the control, in the combinatorial aspects, when we say something is discrete, it means you can count it, something that runs from 1 to 2 to 3, 4, not in a continuous, but in actually singular form. So like this one, you say A, B, somewhat like digital. We say digital and analog in computer science. Okay, that's another definition here. Now we have a theorem. Let theorem now. We can cleanse this to give you a theorem form. Okay, some of these definitions are already in your lecture notes. Theorem. Let be a collection of subsets. Let's call them AI, okay, of S. S or X, I will use them interchangeably. They mean the same, a set. You take a non-empty, a non-empty. Now what I mean, okay? You have a non-empty set, and define define this set inclusion. Okay, we call this set inclusion. Set inclusion. Okay. You find this on S. Okay, then you have the pair this. No, not on S. Sorry, on the collection. Sorry. Then the pair collection with set inclusion is going to be this is going to be is partially ordered. Okay. You want to prove this. Remember, you also have a topology because that symbol there, F with liberated F, it's a collection of subsets, the AIs. So by definition, what I mean by definition, this Fi will be the collection of AIs. Every AI is a subset of S. Okay. So we get a subset S and get all the subsets of the S and connect them together. You form a calibrated F. Is it clear? Then it is on this F that you are going to test your topology axiom, remembering that your operator is set inclusion. Okay. Okay. Yes. So in the proof, you now say number one. It follows we know for every AI in S, of course. But when I say in S, you know, S itself is also contained in this. So by implication, AIs are also in this, isn't it? We can now say that AI is a sub-collection of itself. This is true from definition. Set theoretic definitions will allow that. Every AI is a subset of itself. So this is reflexive property. This property is called reflexive. That means your set inclusion is now reflexive. Okay. So what you need to test now is to test that it is also transitive. Okay, and anti-symmetric. Then you have the definition of partially. I will calculate this theorem. Try to see if I can test the transitivity. Okay, and now number two, if we call this number one. Okay, number one here. Okay, so let's see. Now, for any AI in this, if AI is contained in BI, then AI BI will be contained in AI only if what? AI is equal to BI. For some, remember BI is also in this. So pick two subsets AI BIs in F. Now if this condition, if you find out that AI is contained in B, then BI will also be contained only on one condition, that's it. Are the same. But this definition, this is what we call anti-symmetry. Okay, this requirement is called anti-symmetry. Because if it is symmetric, you don't need to say that are equal. But if you have to say that this condition will hold only if they are the same, then it is an anti-symmetry. The relation is anti-symmetry. So we call it the two are actually anti-symmetry. Then thirdly, we want to test the transitivities. Thirdly, let AI, BI, maybe CI, okay? Then, from set theoretic concepts of facts, I would call it facts or laws, okay, or definitions. You can call it each one you like. If AI is contained in BI and BI is contained in CI, it will imply from these facts that AI is also contained in CI. And this relation is called transitivity. Okay? This follows from theoretic principles or laws or facts, which we all know of. So we make use of that, and so we say the proof is complete. I think it's partially ordered, because this is the definition of partial order. That the relation is symmetry, anti-symmetry. Like some of you are already sleeping, and you can see it's not like that. Okay, definition, clause 6. Now, just like we define topology in terms of open set, we can also define topology in terms of closed sets. Because we notice that the two are almost, what I call it, one opposite to another. But that way, we can construct a closed set from open sets, just like there is a way we can construct open sets from closed sets. So we can do these definitions, and Korostowski's have a way of defining topology in terms of closed sets, using some operator, a functional operator, actually. So we calculate this for. I'll take the next definition now. Closed sets. Okay, closed sets. Closed. Okay. Set is said to be closed if that set contains its adherent points. That's one of the simple definitions. A set is said to be closed. A set maybe A is said to be closed if it contains its what we call adherent points. Then you may ask, what are adherent points? Again, for sets. Okay, adherent points of a set are those points that lie on the boundary of the set, isn't it? Remember, we are talking about sets now, not elements. Sets, not points. In geometrical sense, we are talking about either line segments or closed sets or disks or spheres, as you come to know later. So So that's what we mean. So that if you have a line here, it means this line contains A. So you say this interval is closed because it contains A, contains B. This has adherent points. Okay, this is A. Then we say this is A cap. And sometimes we write it like this. Okay. Or if you are talking about sphere, circle, this is open, but when you include this, then it becomes closed because it contains the points at the boundary, and so on and so forth. These are examples. You can have so many of them. Okay. Another definition is, which I find in your notes, is that A is said to be closed if and only if the complements of A, so S minus A, okay, is open. You can also take this. That means A is closed. A is closed if and only if S minus A is entire. That means an open set. Is it clear? When you take the complement of A from the S, remember your S is the set itself, where you subdivide into AI. So you can even call this AI here. So you have AI now. AI meaning subsets where S is now the collection of AI score. Take S to be the collection of AI. So now every AI is closed if when you take the complement of that with respect to S, you get an open set. That's another definition, which I also find very important, very functional in various in the proof of theorems. You will use this because it is very handy in proving a lot. We have a theorem, of course. Following it says that S have a topological space, and then phi and S are closed. Number one. I will take them one by one. Phi and S are closed. So we shall see how that happens. Let theorem, this is theorem. Let S be S star be a topological space. Okay, number one. S and phi are closed. We saw before that they are open. We are now saying that they are also closed because of the courtesy of this theorem. How do you show this? Okay, proof of this. Now S is in tau, of course. Of course, S is in tau, isn't it? Because tau is a topology, and S should be inside it. But by definition now by definition of what? Of closed sets, S is closed if and only if what? Its complement S minus S is in tau. What is the complement of S in S? It's empty set. But empty set is already in tau because tau is a topology, isn't it? So that means this implies S is closed. Number one. Number two, you can also say that phi, of course phi is also in tau, is closed. We can say phi, you can say this phi is closed for y. If and only if what? The complement S minus phi, but this will give you S because phi is empty, okay, belongs to tau, which you also know because S is in tau, just like phi is in tau. Therefore, phi is also closed. So you have shown that phi is also closed, just like you have shown that phi is open. Okay, yes. Okay, in the same theorem, because we are on the same theorem, we only go to circumpart. Circumpart says A alpha, okay? A alpha. Okay. Maybe M. Okay. It's closed. But let me use S so that I will not be confused. Okay. This is closed for any alpha. Then so let me use if here. So if every A alpha and S is closed for any alpha, so A1 is closed, A2 is closed, so then the intersection of A alphas is also closed. So that's what the second aspect is saying. This is the second aspect of the theory. That if you consider a collection A alphas in S such that each one is closed, then the intersection is also closed. This looks like a definition of topology itself, isn't it? Proof this. Now, A alpha in S is closed means what? S minus A alpha is open. That's what by definition. This by definition. By definition of closed sets. Oh, good. Now, then, what of intersection? Intersection of this S minus A alpha such that alpha is maybe an indexing set. This is the same as what? S minus the union of A alpha. Alpha and indexes. This is by De Morgan's law. Because De Morgan's law says the intersection of the difference is the difference of the union. Isn't it? Yes, good. So this we know by De Morgan's law. Yes. So, but A alpha is closed for any alpha from here, isn't it? So you have no problem saying that this is closed, collection of closed sets, isn't it? If you take the collection of closed set, take the union, take the complement, you get what? Union A alpha is simply what? Collection of what? Of closed sets. So S minus that is actually in terms. That means open. Okay? And if the complement is open, what does it mean? It means this is closed. Okay, this implies S minus intersection. Okay, it means the intersection because this is from the intersection we got this, isn't it? Yes. So the intersection of A alpha S minus S intersection of S minus A alpha, so it implies that intersection of S minus A alphas is actually what? It's actually in tau, which means what? Intersection of A alphas is closed because its complement is open, so that one it is open. So that is number 2. And I think by intuition you can also prove number 3, which says that the union of A alphas is also closed. You just interchange wherever you see intersection, you put union, wherever you see union. In this theorem, you will prove number 3 by the same De Morgan's law. So that one is almost automatic from this. Yeah. So you can use this to form number 3. All I need to do is to change this to union now, isn't it? Then this one will change to what? Union. But the union of S minus A alpha is what? S minus intersection. Isn't it? Yes. So you have here. So this becomes intersection. This becomes intersection. Okay, this becomes union. This becomes. Then you will have proof number 3 that this is also closed. Okay.